Hi and welcome to another video today about the SplineWrap deformer you find in Cinema 4D. What I want to do today is I want to rebuild the SplineWrap deformer inside of Houdini, because in Houdini you don't have a SplineWrap deformer. What you have is a wire deformer that can serve exactly the same purpose. It has one node more to set up. It's a little bit more complicated and more versatile, but it's exactly the same. You can use this, but sometimes it's easier to use something like the SplineWrap deformer, and it's a good exercise in understanding how Houdini works and how you can use it to build tools. But before we start, let's look at Cinema 4D and let's see what the SplineWrap deformer does. What I have here is just a spline. I drew this spline in Cinema 4D and put it in an extrude object such that I create this object here. I modeled this little bump on top just to see the orientation of the object easily. So I go to Deformers and create a SplineWrap deformer. If I do so, I get this object here, and because this is an extrude NURBS, I put it in a null, and if I now put the SplineWrap deformer in here, I see that it conforms to the extent of this object. Now in the attribute manager, what I can do is I have this rail object here that I drew, and what I want to do is I want to make this object follow this rail. So I have to specify the rail here in this spline link field. Now this looks all weird, and that is because, let me turn the deformer off for a second. As you see, the direction I want to conform is Z. And by default, the SplineWrap deformer uses positive X as the direction. So if I switch this to positive Z and turn it on again, it does what it is intended to do. So basically what it does is it takes one of the axes of the object, in this case Z, because we specified it, and instead of using a straight Z, it uses a spline instead, keeping Y and X transformations the same. By doing so, it deforms the individual segments of the input objects to the spline. Okay, now that we've seen the SplineWrap deformer in action in Cinema 4D, we want to build it in Houdini. But before we dive into Houdini and start creating this tool, let's first dive a little bit into the theory and do some sketches to make sure that we understand what we are actually trying to build. I will do these sketches in 2D because it's easier to draw for me and it's easier to understand for you, I assume, and the principles are exactly the same as in 3D. So what I want to do is I have an object. Let's say it's this box here, and this object, let's give it some subdivisions because otherwise it will not deform, and I have a spline. And what I want to do is I want to conform this object to this spline here. Well, first of all, I have to recognize that both of these objects are living in a Cartesian coordinate system. So let's say here this is the origin and this is the x-axis. And we have a y-axis too, because we are in 2 dimensions now. So I have points with Cartesian coordinates, and I have points with Cartesian coordinates that define this spline. As you probably know, if we assume that this is a B-spline or a NURBS curve, these points might look like something like this here. So what I want to do is I have this x direction of the object, and I have the y direction of the object. And now I choose the x-axis to no longer be straight, but instead I want to use the spline as a new x-axis. The translation in the y-axis should stay the same. If I do this, these points on the very left of the object will end up on the beginning of the spline, and the points on the very right will end up at the end of the spline. So these points here will translate to somewhere here, and these points here will translate to somewhere here. And in the middle, we are in the middle of the spline, and these 2 subdivisions will end up here and here. And if we connect the dots, we get something like this. This is my goal. I want to transform all of these points to here. How can I do this? First of all, I need a way to determine the position in Cartesian coordinates along the spline. Fortunately, a spline is a function in 3D, a parametric function. And that makes it easy to get the positions along the spline. This function looks something like this. The vector xy in our case, because we are in 2D, is the function, let's call it S for spline, of the parameter u. And this parameter u is between 0 and 1. Just because it's easier to work like that. So that means if I put a u value of 0 into this function, it gives me this location here, the very first point on the spline. U is 0. If I put 1, I end up at the very end of the spline. Here u is 1, this point here, and in between it interpolates. So if I choose a value like 0.5, I will be somewhere here, u 0.5. This is very, very good to work with because now I can express the locations on this spline in terms of u. I can just say, well, 0.5 halfway along the spline, one end of the spline. And here my object needs the same parameter such that I can somehow correspond these points to the points on the spline. But it does not have a parameter because this is just an object, so it's just Cartesian coordinates. If this is 1 unit of x, this is maybe an x-coordinate of 1, and this is probably an x-coordinate of a little bit more than 2. These values are not very useful for me. So I need a way to somehow parameterize this object. So I have to transform, or I have to find a way to express the location of these points along x in terms of a parameter 2. Then I can just use this parameter to find the same location on the spline and use this information. How can I do this? Well, at the moment this object is expressed globally. So the coordinates of the individual points tell me where these points live in the world coordinate system. But what I want to do is I want to express at least the x value in terms of the extent of the object. Because what I want to do is I want to give a new parameter 0 to all the points that are on the very left of the object, and I want to give a parameter 1 to all the points that live on the very right edge of the object, because I want the left edge to be here at the beginning of the spline and the right edge to end up here at the end of the spline. So what I need is the extent of the object. And every 3D program has a very easy function to find the extent of an object, and that is a bounding box. So what I want to do is I want to find the bounding box. And the bounding box is nothing but a cube that contains all the points of the object. So in our case, it would be a cube like this, that is just containing all the points, just fits exactly and very tight around the object. And I can get this from the 3D software, be it Cinema 4D or Houdini. And now I can get the information where the minimum x value of the bounding box is and where the maximum x value of the bounding box is. And if I now compare the actual positions of these points here to the minimum and maximum values of x of the bounding box, I can do a fit range and I can express these positions relative to the bounding box. You can easily see that the position relative to the bounding box of this point here is 0, and the position relative to the bounding box of this point here is 1, because it's just one bounding box along the x. Same holds true for the topmost points, because they only differ in y, not in x. And the values here in between are interpolated again, because here we are halfway through the width of the bounding box, so we get a value of 0.5, and here we get 0.25, here we get 0.75, and this holds true for as many subdivisions as I have. And now you see that I have a parameter suddenly that works exactly the same as on the spline. I have a parameter that tells me the length of this object on a scale of 0 to 1. So now I can correspond these points here to locations on the spline. I can say, if this parameter here, let's call it u2, if this is 0 on the object, then please use the location that I find here if I put 0 into this formula instead of the x-axis. And do the same for all the values of u. So I can just take this parameter that I found on the points, put it into this formula, get the new location, and move the point there. This is the principle of the SplineWrap deformer. But unfortunately, it does not stop there, because this is only location. If I do that, what I get is I move these points over. So let me switch to black again. If I take these points and move them to the new location, they will end up like this, and these points will end up like this, and these points will end up like this. Like so, like so. You see, we don't need only location, but we will need somehow a way to figure out rotation along the spline too. Fortunately, the parametric nature of the spline function comes to rescue, because we not only can find the location along the spline, but we can find the derivative of this function too. And the derivative gives us the slope of the tangent line. This way we can find the tangent line corresponding to every location along the spline. Let me redraw the spline, like so. That means we saw earlier that we find the location through the parametric spline formula, S of u. And now what the mathematics of the spline formula allows us to do is we can find a new vector that is the derivative of this function. And this vector looks, in this case, as this is a vector valued function, something like this. So at this location, u is 0, we get this tangent vector. And we can calculate the tangent vector at every point along the spline, like so. And you can see that these tangent vectors give us the orientation of the spline. And we can use this orientation, these orientation vectors, to not only move our points, but rotate them at the same time. We can do so if we do the cross product. We can create an orthogonal vector to these tangent vectors, the bitangent, that might look like something like this. And these vectors are orthogonal. And now we have a system, a coordinate system that moves along the spline. And we can use this coordinate system to transform the points to the spline. And by transform in this case, I mean a linear transformation, so a movement and a rotation at the same time. So the last bit that we are missing is to think about how can we do a linear transformation on points. In 3D, the easiest way to do a linear transformation is to use a matrix. This is linear algebra, and a matrix encodes a translation, rotation, and scaling, even skewing and other transformations. And a matrix is just multiplied by a point, and it will transform this point to a new vector space, and by doing so it will move it, rotate it, and scale it. So the math behind it is a little bit complicated, but the good thing is you don't have to care about the math. It's just important to know if you have a point that has 3 coordinates, x, y, and z, and you have a matrix M. This matrix consists of 4 vectors. The x-axis, I draw the matrix, or the space of the matrix, the vector space. The matrix spans here with vectors, so you have 3 vectors, x, y, and z. And you have a 4th vector that tells us where this matrix lives. That is a translation vector. This is the matrix. And a matrix is denoted by a capital letter. And if you now take this point P and multiply it by the matrix, so M times P, it will move the point to here and rotate it such that it's rotated like these vectors. That's basically it. So what we can do is we can take the tangent and bitangent that we generated, create a matrix out of them, use the location to augment this matrix, and then just multiply the matrix by the points we originally had, and the point will move to the spline and will be rotated to follow the spline. The only thing is that the points are not at the origin. So I have a matrix encoding a certain translation, but the point of my object, remember my object sat here, somewhere here, and my origin was here, down there, with x and y. So there is already a translation. And if I now translate again, I will end up not on the spline, but somewhere off, because these two translations add up. So what I have to do first is I have to first move these points back to the origin and then multiply with the matrix. And we will do just that. So now it's time to jump into Houdini and try to apply what we just saw. So here we are in Houdini. What I already did is I exported the objects I had in my Cinema 4D scene, the contour spline and the rail spline. I did so using the Alembic format because it's the most easiest to get splines over from Cinema 4D. And if I import an Alembic into Houdini, I get an Alembic delayed load primitive, which is not geometry I can edit, so I appended an unpack node to make this actual geometry. It is very big because in Cinema 4D we have a base unit of 100 and in Houdini 1, so it's 100 times too big, so I added a transform node and transformed it down. And here is the spline from Cinema 4D. But this spline is open. That's why I use a join node and tell this join node to wrap last first. Another possibility would have been to use an ends node. It does the same. It closes the spline and you see that it's closed because it's now shaded. It's now just a polygon. And then I used poly extrude to extrude it and give it some subdivisions because we want to prepare this to deform to the spline later. And then I created a null, named it in object, and this is my first input basically. The second input, same procedure. I imported a very big spline from Cinema 4D and unpacked it, transformed it down. This is my rail I drew in Cinema 4D and created another null called in rail. So I have two objects in Cinema 4D language. In here it's all inside of one geonode, of course. That can be used to feed the tool we want to create. That takes this rail and deforms this object here, the in object, to the rail. So the next thing is what we want to do is we want to start with parameterizing this object. So remember, to do this, we want to find the bounding box and then fit the points to a range of 0 to 1 to find the parameter. Let's do this using a wrangle. So I append a point wrangle, find parameter, and in the code section here, we want to find the bounding box. So let's switch to the documentation, vex functions, and I type bb for bounding box. Let's see what it gives us. Here is get bounding box. Sets two vectors as a minimum and maximum corners of the bounding box for the geometry. That sounds useful. But down here we have an even more useful function called rel point b box. This returns the relative position of the point given with respect to the bounding box of the geometry. That is exactly what we need. It not only gives us the bounding box, but it automatically creates a relative position for the points. So this is exactly giving us our parameter we are looking for. So let's use this. Copy the function here and switch back to the Houdini. So paste it here. Let's directly write it to an attribute. And I call this my u is rel point b box. The input number is 0 because it's the first input. And now we want to search for a position, and that's at p, the position of the current processed point. But wait a second, because rel point b box is returning a vector. So it's giving me 3 values relative inside of the bounding box, but I'm only interested in z. Because I choose to use z like in Cinema 4D instead of x that I used in the example. So what we can do is this whole function call here will be exchanged for the resulting vector. And with vectors I can use dot notation to directly read the components. So I can just append .z, semicolon, and this will give me only the z component of the resulting vector. So this here gives me, if I now make this active and have a look at the geometry spreadsheet, I have the my u value, and as you can see, it ranges from 0 to 1. Now that we have the parameter, it's time to care about the rail, which you see here. The first thing I want to do is I want to create a resample node. Just because what's coming in is a spline. And as you can see here, the points are not distributed evenly. And I want to distribute the points by arc length, meaning all the points should have the same distance from each other. So this corresponds to the uniform subdivision mode in Cinema 4D. If I connect this resample node, I get exactly this. As you can see, I move closer here. This is before, this is after. And this has to do with the parameter measure along arc, and this is the length. And here you can exactly define how big the distance between two concurrent points is, as you can see here. Now I have a nice uniform spline to work with. Now that I have this, what I need to create is tangent vectors and bitangent vectors and normals. So I have to create a system along the spline that I can use later to translate these points over. And the most straightforward idea to do this is to use the polyframe node, because polyframe does exactly this. It creates a frame. So if you look at the parameters of the polyframe node, you see that it's creating a normal and saving this normal to an attribute called n. Then you have the tangent that is saved in tangent u, and you can create a third vector, the bitangent, saved in tangent v. And you can choose to make this frame orthogonal, and you want to make it orthogonal because you want to use it as a matrix, and this has to be orthogonal. I already created visualizers for these three vectors such that you can see them, and here you have them. You have the tangent, the bitangent, and the normal. The thing is that the polyframe node is not using an algorithm that is called parallel transport. It's using something else to figure out these normals, and the frames are orthogonal, but they are not varying smoothly with the curve, and the normals are not, or the tangents are not always in the direction of the curve. This is not the best method to create a framing for this curve, so meaning axes here on all of the points of the curve. So I searched for another way to create this framing, and I came up with another idea. In Houdini we have a node called sweep. The sweep node, and what this sweep node does is, if you middle click on the point, it needs a cross section, a backbone, and you can supply reference points. And what it does is it takes primitives and sweeps them along another primitive. So let's quickly create something. I choose to create a circle, make it visible. There it is. As I want something square, I go to the circle, switch to polygon, and give it only 4 divisions. And now I append a transform and rotate it over 45 degrees, such that it's parallel to the ground plane. And then let's quickly scale it down to be smaller. Now I can use this here on the first input and supply, get rid of the polyframe node and supply the curve as a second input. And let me turn off point display and the visualizer. What you see is this. Look at this. It's sweeping these polygons along the curve. And as you can see, it's doing this in a very beautiful fashion. So it's varying very smoothly, even here where it's going Y up. It's a very, very smooth rotation of these individual planes. The thing is that I cannot directly use this to generate vectors, because the sweep node has no options to generate vectors from this sweep operation. So you cannot, like with the polyframe node, you cannot directly create attributes that you can use as a matrix to transform points. So I create another wrangle, And I just steal this information from the geometry that is created. Let's call this get framing, because this is what I intend to do. And I have attached it to the wrong node, because what I want to do is I want for every point on the original spline, I want to derive these 3 vectors generated by the sweep. So what I want to do is I want to feed the original spline into the first input of this get framing, and I want to run over all the points of this spline, and as a second input I supply the sweep, because for every point of the original spline I want to search for the vectors the sweep generated. So the first thing I need is I need all the points of these individual planes. I have one of these planes for every point on the original spline. I have this spline here, and you can see for every point on the original spline, the sweep operation created one copy of this polygon. And what I want to do now is I want to use the points of these polygons to derive the vectors, because this edge here corresponds to the y vector. This edge here corresponds to the x vector. And if I do a cross product between these 2 vectors, I get the vector, or the normal. This is what I intend to do. The good thing is that the numbers of these points here, the point numbers, correspond directly, as you can see here, 0, 1, 2, 3, and so on. They correspond directly to the primitive numbers of these generated planes, 0, 1, 2, 3. So it's easy for every point to find the corresponding primitive, and this is what I want to do. But it's not only that I want to find the primitive that is create from this point, but I then want to find the points that are included in this primitive, because I want to use these to create my vectors. And there is a very handy function, back to the documentation. This function is called, if I search for prim, you have prim points. Returns the list of points on a primitive. This is exactly what I want. It returns an array of all the points that are included in a primitive. And as I know the number of the primitive, I can derive or get all the points that are part of this primitive. So let's do this. I paste what I copied. I is missing. Make the get framing active. Of course I get an error because this is not valid. I want to create a variable to hold my returned array called my points. And this variable should hold whatever prim points returns. The geometry I'm looking for is, in this case, 1, not 0, because it's the sweep geometry that's coming in input 1. And the prim num is fortunately exactly the same as the point num, so I can just use pt num. And now I get an array of point numbers, integer point numbers, for every point here. And I will have 4 entries in this array for every point, because remember the sweep consists of individual planes, and every plane has 4 points. What I want to do is, if I quickly display the point numbers, I want to find this vector here between point 3 and point 0, and I want to find this here between point 1 and point 0. And you will say, well, this works for the first plane, but what regarding the second one, there the point numbers are different. But that's not true, because these are the point numbers on the geometry, but we are working with this array, and this array will always start at 0 and will always go to 3. To find the vectors between the points, we want to subtract the points one from the other. And to do so, we need the actual point positions. At the moment, we only have an array of integer numbers that are defining the IDs of the points. So what we need is another expression to find the position, and this is a point expression. No, not this box here. Let me go back and put point into this box, and I will end up with this point expression. And the point expression allows me to search for any attribute on a point. if I have the point number, and I happen to have the point number. So again, let's copy this definition and switch back to Houdini. Now let's look up the position of point 3. So paste this here, get rid of the type. My geometry is still 1 because I'm dealing with the sweep geometry. The attribute name is just P because I'm interested in positions, and the point number, and now it's getting interesting, the point number is an integer referring to the ID of the point, and in my case this is whatever integer is returned and stored in this array at position 3. So I will put my points, so the array, and then square brackets 3. That's the third point that I find in this array, or the fourth point because it's 0 based. Now I have one of the points, but I need a second one, and I want to subtract them. So, because I want to find the vector between them. So let me just duplicate this. And in the second call, I use the first entry of this array. Because, let's switch back to this, you see this is 0.0, this is 0.3, and I want the vector between these two. And I want the tip of the vector to point to 0.3, or the point with the index 3. And because vector subtraction has a rule of tip first, that means the vector always points to the first entry of subtraction, I start with the third entry here. This is my first vector. Now I want to normalize it, because I need normalized vectors for my matrix later, and I want to store it in a variable. In my case, I just call it x. Doesn't matter too much what you call it. And then I do exactly the same thing again for the second vector. Just that I now find the difference between the first entry and the 0th entry, and I store this in y. And now I need a third vector, the vector that is pointing along the spline. And the good thing is I can easily find this by using a cross product. So vector z is just cross the other two. So x and y. And now I have my 3 vectors, so what's left is to store them in attributes to use them. And I thought it might be a good idea to just use a convention that the polyframe uses. So I say the normal will be the vector z, then tangent to u will be the vector x, and tangent v will be the vector y. And because we are creating these attributes, it's a good idea to tell Vex that these are vector attributes. Just put a v in front of the attribute. No, not vector, just v. V, that's it, and a third v here. And now we should have here is a little error because I forgot to put the equal sign. And what we now should have is, if we turn back on our visualizer, look at this, now we have these vectors, these systems here on every point. But if I zoom out and go to a different location, let me turn off all these numbers so that you can see that better. It looks far better than the polyframe because it's now using parallel transport, because the sweep is using parallel transport. And now we have a very beautiful framing for our curve that we can use to find, that we can use to transform the points of the object and to finish our deformer. Now we pretty much have everything we need to create the deformer. So what's missing is the last wrangle. So let's create one, point wrangle. And this one is actually called, let's call this one SplineWrap. Because this is doing what we intend to do. And what it needs is, as a first input, it needs this first stream, which is our object. And as a second input, it needs the framed curve, which is this here. Okay, now it has everything it has to know. There is one thing missing, because here this object is still a three-dimensional object. And remember what I told you in the explanation section about the pre-transformation. So these points are already transformed along the z-axis. But I am only interested in the x and y translations. The z translation is not interesting because I want to translate these using a matrix to the spline. So what I do to fix this is just create another transform node and put it here in between and scale them to 0 in z, like so. Now I got rid of the z component of the positions, basically, with a little trick, and I prepared this object to use the matrix multiplication to move it over. Here in the SplineWrap, I now can create my matrix and do the matrix multiplication. To do so, I have to sample the geometry that's coming in on input 2 or input index 1, because this geometry is has the framing, so the system, the 3 vectors on every point. And on this geometry that's coming in on input 0, I have the parameter. So what I want to do is I want to ask geometry of input 1 at the parameter coming in input 0, what is the vectors there and what is the position on the spline. This is what I want to do. So let's see which vex function is there to help us find this information. And there is a very, very powerful function called primuv. Let me look it up. Evaluates an attribute on a primitive at a certain parametric UV position into a variable. That's exactly what we need, because what we have is we have a parametric position. We only have U because we are dealing with just a polyline. It works for U and V on surfaces too, but in our case U is sufficient, and it will, if you give it the parameter, it will return the interpolated information and store it into an attribute. That's exactly what I outlined in the explanation section, and that's exactly what we need. So let's copy this and let's switch back to Houdini and use it. Now back in Houdini, how can we use this? Let's first paste it. There is 4 things I want to query about the geometry coming in on input 1. That is the position along the spline and then the 3 vectors, n, tangent u, and tangent v. Let's start with the position. So let's create a new variable, vector variable. Let's call it rail p for rail position, and this will be geometry input 1. The attribute I want to query is p, and then comes the primitive number, and the primitive number is just 0 because this polyline here is just one polyline, so there is only one primitive in this geostream. And now I have to create a vector that is using my u attribute. To do so, I need the set function, because if I want to create a vector dynamically, I have to use a set function, and as a u component of this vector, I will use my u. The other 2 components are just 0, because we are dealing with a polyline here, and so only the u component is relevant. So this is rail p. Now let's just duplicate this 3 times, and let's call it rail x, rail y, and rail z, and these 3 variables will store the 3 orientation vectors. And I query tangent u, and I'll query tangent v, and I'll query n. And now I have all the components I need for my matrix. It's time to create a matrix, and that is done in Houdini with the matrix keyword, and then I have to give the matrix a name. Let's name it transform, and this will be the 4 vectors. So rail X, rail Y, rail Z, and last comes the translation. Please note, if you are programming in Cinema 4D, there it's the other way around. There the translation comes first. It's the first vector. So the matrix order in Houdini is the other way around. First the 3 orientation vectors and then last the translation. So, and now if I did everything correct, the last thing I have to do is to update the point positions, and I can do so by just multiplying all the points by the matrix transform and storing them back into the position variable. So let's see if this works. And yeah, look at this. Here you have it. The normals are not correct. So let's quickly append a normal node. And here you have it. SplineWrap deformation, exactly like in Cinema 4D. So it's taking this input object and it's transforming it to the spline, and we created a framing for the spline. And this setup already gives us a lot of options, because now we can go to the sweep node, and on the sweep node we see that we have scale, twist, and roll parameters. So what I can do is I can roll my sweep, and of course, because the curve framing will roll, I can, using this, roll my curve, like with the Cinema 4D counterpart. So it's a very flexible setup. Of course, it does not have all the features of the Cinema 4D thing, but it's easy to extend on this setup and build in everything we saw in Cinema 4D. And then we can save this as a digital asset, and in the future have it as an option. If we don't want to use the wire deform, we can use this simplified thing.